The ideal gas law. It's totally fake. Fundamentally, it's theoretical. And yet it's the most famous equation in almost all of chemistry. The reason that it's made up and it doesn't really exist is because it ignores a lot of real things. Intermolecular forces, for one. We know about intermolecular forces, hydrogen bonding, dipole-dipole, and London dispersion. Another thing that ideal gas law ignores are things like collisions. The fact that molecules will run into each other and run up against the walls of things. So the ideal gas law is very, very, very situational, and yet it tells us a lot of valuable information. Because it can tell you properties of a gas without having to change anything about it. It can just tell you, hey, if you know the pressure, the volume, it can tell you temperature. It can also tell you moles. We're introducing moles into this guy. And we're using a constant. Now, constants should not be new to you. You've used them in math. Anytime you've done y equals mx plus b, the b was a constant. It just means it's a number, and it will always be that same number. Okay. Now, the ideal gas law is very specific on the units that you use for it, which is why I listed them out. Unlike the combined gas law, which we could use things like torr or millimeters of mercury or milliliters and things like that, the ideal gas law says we have to use certain units. Volume has to be liters. Pressure has to be atmospheres. N stands for moles. That's new. The R, that's your constant, and it's just always a number, 0.0821. I wrote that on the slide. And your temperature, which has to be in Kelvin. That's why we did temperature conversions yesterday and pressure conversions, because you're going to have to do those in order to get to the right unit for the ideal gas law. Cool. It relies on a lot of the same properties that we just used in terms of the fact that pressure and volume are indirectly proportional or inverse related. And temperature is directly related to both pressure and volume. These word problems will look a little different because they're only going to give you one of each variable instead of doubling them up. So that's an easy way to tell, hey, I need to use the ideal gas law here. Sometimes the problem will even say you're using an ideal gas. Okay? Make sure you pick up on those key clues. Look at this first one. It says how many moles of gas are in a 4.50 liter container at 1.20 atmospheres and 300 Kelvin. We start these out just like we did the other ones, by making a list of my givens. 4.50 liters. Liters means volume, so I know my volume is 4.5 liters. Atmospheres means pressure, so I know my pressure is 1.20 atm. And I know my temperature is 300 Kelvin, because Kelvin means temperature. It's asking how many moles, so I know I'm finding moles, which in my ideal gas law is represented by a little m. And now I'm ready to use my equation. The ideal gas law equation is PV equals nRT. Pressure has to be in atmospheres. If I look at my pressure, I see it's in atmospheres, so I'm good to go. Volume has to be in liters. My volume is in liters, so I'm good to go. I'm solving for moles, but then I have R, but I don't have a number for R. R is your constant. That number is always the same. That's why you wrote it on the first slide. R is the gas constant for atmospheres. It stands 0.0821, and it will never ever change. And finally, my temperature has to be in Kelvin. I see that it is, and so I have 300. It's a matter of doing my algebra now. I need to get n by itself, so I'll divide both sides by the quantity, 0.0821 times 300. And I would get my answer. I get 0.219 mole. Let's do one more. What is the temperature of an ideal O2 gas, oxygen gas, if there is 32 grams and it occupies 500 milliliters at 780 torr? Temperature is what I'm solving for because it says what is the temperature. It says I have 32 grams. I know I can't use grams in the ideal gas law, but I do know I can turn grams to moles. So I'll put that there for now. It's occupying 500 milliliters. Milliliters is a volume, so I know my volume will be 500 milliliters. My pressure, 780 torr. Torr is pressure, so I know that goes here. When I'm setting up my equation, I need to ask myself first with my pressure, because that would be my first number, is my pressure in the right unit? No. Pressure has to be in atmospheres for the ideal gas law, but that's okay because I know how to convert pressure because we just did that yesterday. We use a little dimensional analysis. Like so. What do you say? 1.02?
Yeah.
To get 1.02 atmospheres. My volume is currently in milliliters, but I need that in liters so I can divide by 1,000, or 3 spots back for my decimal, and I get 0.500 liters. My moles, I'm in grams right now, so I need to convert that to moles, but that's okay because I know how to do that using some more dimensional analysis. If I have grams of O2, I'll have grams of O2 down here. And I'm turning grams into moles of O2. Whenever I see grams in my grid, I know that's molar mass. The molar mass of O2 is 32 for every 1 mole. Yeah. 32 times 1 divided by 32 is just 1. My R constant never changes, 0.0821. And I'm solving for T, temperature. Do my algebra, get T by itself. Just divide each side by 0.821. See if you get what I get.